Okay, so now that we've taken the poll, you can see most of us have been here for not that much, so which is what I expected. I mean, this is a talk for new people, so I'm glad that you're all here. It's really bright and early for me, and I'm excited to be here. So, okay, let's jump into talking about quantum computing, though, since that's what we're here for. But I thought I'd begin by introducing myself. So I want to say hi to everyone. I want you to know that I'm a fellow newbie, so I started working in quantum computing about 6 months ago. And this is my background. I did my PhD at the University of Michigan in electronic structure, so my background's in chemistry. Then I went on to do my postdoc at Lawrence Livermore National Lab, and I'm currently a quantum chemist at QCware. So I develop algorithms for chemistry applications. I work in software. And this is how to get in contact with me if you want to reach out today. I'll be around in the conference all day, so don't be shy. I promise I don't bite. And let's jump into it. So let's start talking about how quantum computers are different from classical computers. I thought most of you guys would suspect this, otherwise there would be not a lot new to learn. So we all know that quantum computers are going to work differently than classical computers, and we just have to get to the bottom of why that is. So the first thing I want to mention is that quantum computers are believed to solve certain problems faster than a classical computer. And we'll get into more examples of what this means in a moment. So the main takeaway I want you guys to understand is that quantum computing is not going to replace classical computing. So we're not just looking for a faster computer that can solve problems in the same type of framework. We're looking at computers that work completely differently and can solve different types of problems. And that kind of makes it exciting, right? So the reason this has to do with what's under the hood. So basically, quantum computers are going to use quantum principles to perform the computation. So this is a completely new way to compute. So we need to understand what these quantum principles are at play underneath the hood in the computer. So the first thing I'm going to talk about is superposition, and I'll get into more details about this, but basically it's the idea of taking a quantum state and adding it to another quantum state to produce another valid quantum state. So one of the things we need to know is about how quantum computers store information, and it's very different from classical. So in a classical computer, we can think about classical bits. So we probably have seen this before. So classical bits have states that are either 0 or 1. And this is like a very binary way to be. Whereas qubits can take many values. So kind of a superposition of these two things. So that's where the idea of superposition comes in. I'm going to give you an analogy to kind of make this more tangible. So this is one of my favorite analogies that I didn't come up with, but it's from this video on YouTube. So basically, you can think of a classical bit as either side of a coin, so heads or tails, and you can think of a qubit as a spinning coin. So it's kind of in both of these states at once, and then ultimately it's going to land on either one or the other side once you measure it. So this is like a helpful way to think about how qubits store information. So basically, this spinning coin you can think about is a superposition of the weighted sum of these heads and tails state. So the next quantum principle we need to understand in order to understand computation is entanglement. So you can think of entanglement as the idea that the quantum states are correlated to each other, so they can't be described independently. So basically, the state of one quantum state depends on the other. So in our quarter example, you can think about these two quarters as two qubits. So we have these two spinning qubits. And if we measure one of them and the outcome turns out to be heads, we automatically know the state of the other. So for example, let's say that if one measures heads, the other one has to measure tails. So this is the idea of entanglement. And it's actually really important in quantum, and it's what Einstein called spooky action at a distance. So the idea is that basically, even if these states are really far apart, they're still entangled to each other. So both of these both of these things are going to work together when we do quantum computing. So we want to know, how do superposition and entanglement work together? So I came up with another simple example to kind of illustrate this. So here's an example. We have 2 pairs of pants, 2 shirts, and 2 pairs of shoes. So we want to know how many outfits we can make. So you guys probably know how to do this classically, or how to think about this. So does anybody in the chat want to, how would you solve this problem classically? Okay, I'm seeing some different answers. Okay, seems like people have a pretty good handle on it. Yep, so I wrote out the solution because it's such a simple example. So here's all of the different outfits we can make. So many people pointed out it's 2 to the n outfits where n equals 3. So for each pair of pants, we have 2 different shirts we can try, and then for each one of those combinations, there's additionally 2 pairs of shoes we can try. So this is how we can build up all these different solutions. So let's think about how a quantum computer might do this. So each one of these Qs here represents 1 qubit, and on each qubit, we're going to represent a superposition of our 2 choices here. So we have the 2 pairs of pants, the 2 shirts, and the 2 pairs of shoes. Like I said, one of these is on each qubit. So the way the quantum computer is going to represent all these choices is through entanglement. So every single one of those 8 outfits is going to be represented somehow. If you could magically, come up with some mathematical way to entangle these things. I promise no math, so this is the example I chose. So the quantum computer knows all of the solutions to all these outfits through entanglement. And this is kind of the power of quantum computing, is the entanglement. You can probably imagine a scenario where we had, something a lot more complicated, and this would become harder and harder to do for a classical computer. Like I said, we saw in our example, we just, we take 2 to the n, but that space grows very quickly once we have more and more choices. So once we have entanglement, the quantum computer can get to all of the answers. One caveat to this, though, is that we can't measure all of these outfits at once. So each measurement we take is going to return 1 outfit. These superpositions are going to collapse into one state, just like our spinning coin collapsed to either heads or tails. So the idea is that we have to do many, many measurements in order to get to all these different outfits. But if we took a lot of measurements over time, what we'd find is that we would recover each one of these outfits with, since there's 8 of them. And if we weighted all of these equally, we would come up with, all different 8 outfits with roughly equal probability. So we can't measure all the outfits at once. But the quantum computer is able to get to all these different answers. And this is kind of where the algorithmic design comes into play, because the quantum computers, when they're doing the measurement, kind of take advantage of interference. So I'm going to explain what that is quickly. So there's 2 types of interference. There's constructive and destructive. We can see in the constructive interference, we have these 2 waves that are in phase with each other. Basically, what I mean is that the amplitudes are lining up here. In this, that's constructive interference. In destructive interference, you can see they're out of phase. So the amplitudes are kind of out of phase. You can see the peaks and the valleys are at different points. So what this basically amounts to is that in the constructive interference case, the amplitudes add together, so we get a larger wave that has, in this case, double the amplitude. And in destructive interference, the amplitudes cancel out, so we're left with the straight line. So the idea in quantum is to come up with a way to make the correct answers interfere constructively with each other to make something like this, so something that can be measured, and then to make the incorrect answers interfere destructively and to kind of cancel out. So this is how quantum computers take advantage of interference. So there's a lot of exciting new application areas in quantum. You're going to hear about a lot of them today, I'm assuming. I'm excited to hear about a lot of them. So I'm just going to name a couple of the examples. So the first one's cryptography. So basically, keeping like your bank information secure and things like that. There's very good quantum algorithms to factor prime numbers. This is the area that I work in, so simulating quantum systems. Super exciting for me. So basically, a lot of molecules or a lot of chemistry and physics applications have to deal with quantum systems, electrons, nuclei, things like that, and we can simulate a quantum system using a quantum system. So, and then finally something like optimization. So something like our traveling salesman problem, something like inventory, how to ship things efficiently. Those are the kind of applications that some industries are interested in. Like I said, I'm not qualified to speak about, every single application. I'm a little bit qualified to speak about this one, simulating quantum systems. But yeah, so that's my favorite. What areas are you guys interested in? Can answer in the chat and get to know each other. Seeing a lot of optimization, machine learning, biology. So yeah, hopefully we'll get to hear some really good talks about all this stuff today. Cybersecurity, machine learning. Yeah, so all kinds of cool stuff. Yeah, awesome. Okay. So I told you all these very, kind of conceptual things. And I said like, quantum's going to be able to help all these areas. So basically we need to know what's the catch. And the biggest catch is that there's still a lot of work to do. So there's a lot of work to do in both hardware and software, and these two things are pretty coupled to each other. So I'm going to talk about a little bit about each one of these things. Like I said, once again, I work in software, so there's many, many people here who can talk to you about the hardware that are giving better talks than I will today. So first of all, I was mentioning this qubit, and I was saying, it's like a quarter. But of course, we know that qubits are actually something a little more complicated. So they're real quantum systems, and there's actually more than one way to represent a qubit. So there's all these different manifestations of them in hardware. There's photons, there's ions, things like that. And as of right now, there's no one technology that seems to be winning. So there's many ways to build this qubit, and the software is dependent on the hardware. So these two things are definitely coupled to each other. And there's a lot of work to do in both of these areas in order to build better quantum systems and better hardware or better software applications. What's another catch? Another catch is that all of these, a lot of these algorithms are designed with the assumption that we need fault-tolerant qubits. Basically, what that means is that we have perfect qubits that have no errors, and that's just not the case. So in the hardware space, people are doing a lot of work to build better qubits. In the software space, people are doing a lot of work on error correction, so how to deal with the fact that we're not working with perfect qubits. And both of these spaces have seen some really good progress recently, and I expect more to come. But that's kind of the situation we're dealing with now. We don't have a perfect quantum machine, so we have to take that into account when we're building our applications. And then finally, for the hardware, it would be nice if we could have really large number of qubits. But that's hard to do because quantum systems are hard to keep coherent. So, the current machines we have, while there's been really great progress, they're not quite at the level we would like. So a lot of algorithmic development is under the assumption that we have these really large machines, and we just don't have them yet. So like I said, this is a catch for hardware and software. Building the hardware to have these large number of qubits is tricky, and then designing an algorithm that depends on the number of qubits we currently have is also tricky. So this is good for us because otherwise we'd have to spend our time doing something else, but there's still a lot of work for everyone to do, which is exciting. So like I said, this is an upside and a downside, but we're currently in the era of kind of NISQ devices. So we're looking at noisy intermediate scale quantum devices. So what noisy means, once again, is this idea that we have imperfect qubits. We have qubits that are going to interact with their environment and have some errors associated with them. And we're coming into the space of intermediate scale, so around 50 to 100 qubits. We're not yet at the era where we have thousands or millions of qubits. So I want to leave you with some final words before we start having a discussion and talking about questions. So the expert at anything was once a beginner. This is from Helen Hayes, who was an actress. So these are wise words, even though she wasn't a quantum chemist or anything like that. But I appreciate what she has to say. And I put together some resources for people who want to learn more. These are kind of just my picks. There's so many that it's hard for me to pare them down. But if you're looking for a good book, this is a very technical book that I like a lot. It's kind of like the one that everyone gets recommended, I think, when they come into the field. So Quantum Computation and Information by Nielsen and Chang. Then there's this Quantum Computing for Everyone. So this one's a little less technical, a little more accessible to the non-expert. I bought this for my uncle for Christmas, and he likes it a lot. He's not a scientist, so. There's this really cool website called Quantum Country. It's kind of like a tutorial, and it brings you through all these quantum concepts. And it has quizzes along the way. It uses this idea of spaced repetition, so it'll kind of go back to old concepts and review to help you retain them. And then there's this game that I have on my phone. It's called Hello Quantum. So we probably all spend a lot of times on our phone. So this is a way to learn about quantum while you're playing. But basically, you have to look at different quantum circuits and build them. And it kind of quizzes you. And then here's a couple YouTube videos that I like. One's a TED Talk, and one is just an explanation of quantum computing in 5 different levels of difficulty. Like I said, so there's a level for everyone. And I encourage you all to drop by the QCware career booth today. So I know there's a lot going on today, but if you want to chat with me more, I'll be in the booth during our time, and you can ask me questions then if you think of something that comes up. And with that, that's the end. So here, I'll go back to this slide. Denise, do you have the mic now?
I do. Oh, let me turn on the camera. There's no video. Okay. Well, you guys can hear me, so we'll go with that for now. Do we have any questions? This has been great, and I love the books and resources. So you have 8 more minutes for questions, and I think there should be a lot of questions. And I do want to reiterate to everyone to join. When you go to the career fair, there's going to be company booths at the end of the career fair. And it's a really good time to go and meet people from the company. So you submitted your resumes, but the next step is to go meet people and get to know them. So I want to make sure that all of you budget time today to go visit the individual booths at the career fair and meet people so they can link together your picture and your skills and who you are. So that's really important. So Carolyn is asking Alicia, or not Carolyn, someone is asking you to tell us more about your research. So tell us what you're doing at QCware.
Can you guys hear me? Can we both talk at the same time?
Yeah, we can.
Okay, perfect. Sure. So I work at like I said, I work in software at QCware. And basically what we're trying to do is develop algorithms for chemistry applications and all kinds of applications, actually, but I work in chemistry. We're trying to develop chemistry applications that are going to work on NISQ hardware. So basically the field I work in, electronic structure, has been been on classical computers for a long time, but we're trying to take classical electronic structure methods, find the find the pain point, so find the tough part of the algorithm, and then put that onto a quantum computer, and then help companies solve their particular software issues. So if someone's trying to model a certain kind of system, we design a specific application for that. So you can imagine, some company wants to design a better catalyst or something. So we kind of work with them to think about like the specific type of catalyst that they make, and then we kind of come up with a quantum solution in order to help them solve that problem.
Okay, that's great. Another question is, as someone who's recently joined the quantum revolution, what advice would you have for those following in your footsteps?
Like I said, my footsteps. I've been working here 6 months. They said the best advice I get is try to talk to as many people as you can and learn as much as you can. So kind of get everyone's advice. This way you're kind of immune to things like, all the different hype. So if you go online and read about quantum computing, it's like, oh, it's going to solve all our problems tomorrow. You can kind of get a more realistic picture when you talk to people who actually work in the space. So attending events like this one's a good idea. Just reaching out to people on LinkedIn. Like I said, studying more. So all of these resources are great ways to get started. Stuff like that.
Great. And how did you handle the learning curve as a newbie to quantum? So I see these resources. Did you start reading? What worked for you best?
Okay. I'm still handling the learning curve, to be honest. So one thing was that, like I said, I did my PhD in chemistry, so I actually had a background in quantum. I wasn't starting from the ground up. So having a really good education in quantum is crucial, I think, if you want to actually do work in the software or hardware space. So even going back to physics 101 kinds of things, like make sure you have a really solid foundation in that. And then once you do, like I said, this Nielsen and Chang book is kind of like the Bible of quantum computing. So that's what I would recommend next. Make sure you have the fundamentals there. And then once again, just talk to people, get to, talk to people, read the new research that's coming out, get to the bottom of what's going on in the space.
That's great. I know it's a challenge to start learning, and I would tell everybody to jump in and read. And for me, what really helped is to look at, you have books and videos and websites, and to look at the different kind of ways of presenting the same information, and it starts to then click. So I encourage everybody, look at the Hello Quantum game and try to do that. Try different things to get going. One of the questions is whether it would be possible for you to share the slides, so we can talk about that later.
Oh, yep, of course.
And I guess the other question is, how did you get interested in quantum, and what was the interview process like?
Oh, okay. So like I said, I did my PhD in electronic structure, so I'd have to go back when I was an undergraduate, basically. So I did my undergraduate in chemistry and math. Those were kind of my two favorite subjects. And I began studying theoretical chemistry then. So that's kind of when I got really interested in quantum. I went on to do my PhD in electronic structure, which I loved. And then I went on to do my postdoc. So I spent a lot of time learning about electronic structure. And then, as I was coming up through graduate school, my postdoc, there started to be a little bit of buzz about this quantum computing stuff. So I learned a little bit about it. Like I said, just in passing, basically. And then in my postdoc, when I started looking for a job, people at the lab were giving presentations about it and started to, ramp up and get a little bit more serious. So I started learning about it more seriously. The interview process was interesting. Like I said, looking for a job is always stressful. But the best advice I can give is just put yourself out there. Once again, talk to people. Like I said, I had a great experience interviewing with QCware. Everyone there is very nice. I interviewed with a few other companies that I won't disclose, but they were also very nice. So like you said, just put yourself out there. Don't be shy to people. Yeah.
That's great. Thank you so much, Alicia. Do you have any last minute comments or words of wisdom?
Words of wisdom. He said it's so weird that like I'm on here and people are asking me for wisdom. But I guess my wisdom is like I said, have fun today. Don't take yourself too seriously, but try to learn as much as you can today, I guess.
That's a great thing. Thank you. So everybody, what we're going to do next is on the bottom left-hand corner of your screen is a red button. And when you click that red button, you go back to the kind of schedule page, and then you need to click to enter the next event. And I'm going to log off and see if I can get my camera to work. So I will see you guys in probably a minute at the next event, which will be the opening. So look forward to seeing you there. And thank you so much, Alicia. That was great. And we'll see you in the booth later today.
Yes. Thank you for having me. Thank you for tuning in, everyone. See you soon.
Thank you.